might as well just get started. I'll introduce myself. So this week I'm going to give you a very brief introduction to a few topics in combinatorial enumeration. Today I want to talk about two things, and I'll go into quite some depth about the second one: the Lagrange implicit function theorem and exponential generating functions. Together, these two things provide an extremely rich and flexible technique for solving enumeration problems, counting things. And of course, I don't want to dwell on the formal justification of the technique, and I'm not going to get into the foundations of it. I just want to sort of show you some sample calculations to illustrate the method. And I think if you do a reasonable amount of symbolic pattern matching, you'll get a good feeling for how it works. Then tomorrow, well, everything else that I wanted to talk about. It's just going to be a smorgasbord of things, a taste of this and that, some combinatorial identities that I find interesting and I think might have some relevance to statistical mechanics models. And, well, that's for tomorrow. So today, in brief outline, this is what I had planned. Lagrange implicit function theorem, exponential generating functions. The simplest non-trivial calculation in the theory is that there are n to the n minus 1 rooted trees on a vertex set with n elements. You can use exponential generating functions to provide a combinatorial proof of Lagrange theorem. Another example, some more stuff, and it's way too ambitious. So I'm going to just pare it down to a few examples. And the elaboration of the theory, that would be for week 2 of the course. Basically, I'm covering a month of a graduate course in 2 days.
Will we have another chance at multivariate Lagrange? Or?
Yeah, I will mention multivariate Lagrange first thing tomorrow. Yeah. So, quite by accident, I found this quotation in a paper by Peter Lax in the current issue of the Bulletin of the AMS. It's absolutely perfect for today's lecture. The human mind has never invented a labor-saving device equal to algebra. By implication, the human mind did not invent algebra. Right? I wonder if Willard Gibbs did that on purpose. So here's the Lagrange implicit function theorem. I've got a commutative ring K of coefficients, and you have to assume that it contains rational numbers. I've got two formal power series, F of u and G of u, and they have the form given there. That's just a generic form of a formal power series in the indeterminate u. And that K double brackets u is the ring of formal power series. So these are power series with no convergence criteria on them whatsoever. You assume that the constant term of G is non-zero, just because if it's 0, the whole situation is trivial. The first statement is that there's a unique solution to this functional equation. R is equal to x times G of R, where all the algebraic symbols are interpreted in the way you would expect algebra to work. So it's interesting to know that there's a unique solution, but you can actually say what that solution is, term by term in the Taylor series expansion, if you like. For that formal power series that satisfies that condition, the constant term is 0, and all of the other coefficients are given by this hairy-looking formula. So this x to the power n in square brackets means it's an operator that you apply to a formal power series, and it says extract the coefficient of this monomial from this power series. So the left-hand side is the coefficient of x to the power n in this power series. And it's equal to 1 over n times the coefficient of u to the n minus 1 in this power series. And the right-hand side is not, it doesn't involve r at all. There's nothing unknown. It's all input data. So this is telling you something about the unknown implicitly defined power series R in terms of the input data. Well, it's an abstraction. There are several proofs. Probably the most familiar one would be using complex analysis and the Cauchy residue formula. But that requires non-zero radii. Oh, of course.
There was no F in the state.
Oh, yes. I should have made that clear. In part A, the power series F is irrelevant. This power series R is implicitly defined by the power series G. But if I want to know, but in part B, this is telling me the coefficient of x to the n in this function of R. So it's just some extra flexibility in what you can understand using part B.
So if you want, you could take f of x to be x itself.
Yes.
And get the coefficients of R.
So that's the standard application. The first application is to take f of u to be u, or so the coefficient of x to the n in R of x, then f prime of u, well, it's the derivative of u with respect to u, it's just 1, so that goes away. So I probably, for this talk, should have restricted attention to that case, because that's the only case that I'll use. And in fact, I'll only use it once.
What's the difference between A and B? I see.
A is just telling me that R of x exists. There's a unique solution to this. And B is telling me what the coefficients of that solution are. In fact, what are the Taylor series coefficients of any power series function of that solution? By the way, if you're busy taking notes, there's no need, because all these slides are going to be up on the web in a week or two. Oh, well, yes?
What's the relation of u? What's u?
I just used a separate variable for u and for x for no particularly good reason. I just wanted to use the variable u here when I'm giving the input data and the variable x for the output data, just because I'm substituting R of x for u. So there is,
in the second one, in the expression for the coefficient of R.
in this one?
Yes,
Yeah.
the right-hand side u should.
Well, each side is just an element of the ring K. Each side is just a coefficient. So this f of R of x is a power series in x,
Okay,
and this
so
is a
the
power
right
series
side
in u.
is the coefficient of n power.
Yes.
Power n minus one.
Right. This means extract the coefficient. Okay? So that's the Lagrange implicit function theorem. So there's a complex analysis proof that would probably be familiar to you. And you can abstract the calculus that enters into that proof and prove all of the lemmas of formal calculus algebraically. And then you get the same proof with no convergence criteria on your power series.
Could I just remark, in the complex analysis case, I guess K should still be C, but you can get rid of the non-zero radius of convergence by realizing that if you want the nth coefficient of R, that will depend only on the first n coefficients of G anyway.
So you just
So
do
you might as
polynomial
well let G
truncation.
be a polynomial.
Oh, yeah. Well, that's sneaky. Yes.
Of course it's sneaky.
That's very nice, yeah, okay. And that's essentially what's at the root of the algebraic proof as well. It's that same idea that you get that kind of formal convergence. And there's also a combinatorial proof, which I really would have liked to show you, but it just takes a bit of time, and it has some ideas in it that aren't completely germane to the main ideas I want to get across. Okay, so that's the Lagrange theorem. You can just put that away for a little while. Exponential generating functions. Basically, it's a way of systematizing counting problems that all have a similar structure. That structure is you have some class of objects that you're interested in counting, say the class of permutations, to take a trivial example that we know how to count already. The class of permutations is some kind of a thing that associates to every finite set some other finite set, namely the set of all permutations on that set. Similarly, the class of graphs. If you give me a vertex set, V, or X, say, then I can hand back to you G sub x, which is the set of all graphs with a given vertex set. So this is a very general framework. The requirements that we have on what constitutes a legitimate class of structures are quite minimal. And then you form the exponential generating function for this class of structures as follows. First of all, just to simplify notation, I'll let A sub n be the set of A-type structures supported on my canonical n-element set. Basically, for this theory, we want every n-element set to be good as every other n-element set. So this is the standard n-element set, 1 up to n. The exponential generating function for this class has this form here. So the cardinality of this set, so the number of A-type structures on an n-element set, and then x to the n over n factorial. And this is the funny part of this definition. The n factorial in the denominator is there so that the algebraic operations on formal power series translate into combinatorial operations on classes of structures in a particular way, so that the algebra of formal power series reflects combinatorial properties, combinatorial relationships among these structures. And I'll give you some examples of that very, very shortly.
Where we should always think about this finite set X to be, these are labeled
Yes.
structures, so, right?
Yes. I mean, it doesn't hurt even to think about them being the numbers 1 up to n. But yes, these structures are always labeled. So I'm not considering graphs up to isomorphism. I'm considering graphs with a fixed set of vertices.
And if you have two finite sets, x and y, and a bijection between x and y, then presumably canonical bijection. Oh.
I'm not getting into that much detail.
But I mean, the point is everything is supposed to depend on the number of elements in the set.
Yes. So I'm going to make minimal requirements on these classes, but there's actually something functorial about it that I'm going to ignore, so don't worry. So the minimal requirements are that the number of A-type structures on a set X depends only on the size of X, and that if you have two different vertex sets, then the sets of structures on those sets are disjoint. So what this second thing is saying is that from a given A-type structure, you can recover the set of vertices on which it lives. And it doesn't matter which set of size n it lives on, there'll always be the same number of these things. So maybe a few examples are in order. So the class of graphs, this is a good starting example. Given a set X, G sub X is the set of graphs with that given vertex set. And in this case, I mean simple graphs, so you're not allowed to have multiple edges. If X has n elements, then there are 2 to the n choose 2 graphs on that n element set. Because for each of the n choose 2 pairs, you can either include it as an edge or not. There are 2 choices for each of the n choose 2 pairs. And the exponential generating function is given there. It's not a particularly useful formula, not that I know of anyway. Well, yes, but I mean, it's not in terms of elementary functions. Class of endo functions is kind of a similar thing. They're easy to count. An endo function is any function from a set to itself. So if the set has, typo here. I guess I'm implicitly supposing that X has n elements here, right? So for each of the n elements of the set X, you have one of n choices for its image. So there are n to the n endo functions, and here's the exponential generating function. Permutations. This is starting to show the theory a bit better because we have a nice formula for the exponential generating function. But again, these are trivial cases where we can count them from first principles. Cyclic permutations. Doesn't take long to convince yourself that there are, if you have a set of n elements, there are n minus 1 factorial cyclic permutations of that set. Just write down all n elements in any one of n factorial linear orders and then wrap them around cyclically. Doesn't matter which of the n places you started in, then you get n minus 1 factorial cyclic permutations if n is positive. If n is 0, you have to think about how many cyclic permutations are there on the empty set. And I claim that this calculation here tells you that there should be 0 so that this formula works. That's teleological, but there are good reasons for saying that there's no cyclic permutation on the empty set. The idea is that a cyclic permutation is a connected component of an arbitrary permutation. Here's another class, the class E of finite sets. E stands for ensemble, which doesn't carry any of the baggage that it does in statistical mechanics. It's just French for set. There's exactly one way for the set X to be a set. So the set of ways that X can be a set is the set containing the set X, which is crazy. It's much ado about nothing, but that's what it is. So there's one way for X to be a set, and here's the exponential generating function for sets. So these, okay, there's one more example I want to talk about. This is kind of an elaboration on the last example. The class of sets of size k for a given value of k. There's exactly one way for X to be a k-element set if X is a k-element set. If X is not a k-element set, then it can't be a k-element set. So this is the class of ways in which X is a k-element set. And here's its exponential generating function. So this technique is handling all of these disparate classes of structures in a unified way. And we're getting sensible algebraic analogs of these combinatorial things. Well, for the last few examples involved the geometric series, logarithm, exponential, and there's this obvious algebraic relation among these series. If you think about the classes that these were attached to as exponential generating functions, this is the generating function for permutations, for sets, and for cyclic permutations. So this suggests that there's something going on at a combinatorial level, not just at an algebraic level, that there's a relation among the classes. And I'm not defining this notation yet, but the interpretation is that a permutation is equivalent to a set of cyclic permutations. So now I want to start thinking in pictures. So here's my set X. This is, you might think of it as the numbers 1 up to 15. They're labeled, but I've suppressed the names of the points. So a permutation is equivalent to a set of cyclic permutations. I mean, there it is. It's a set of permutations, a set of cyclic permutations. There's 6 cyclic permutations. They're pairwise vertex disjoint. The union of them covers the set X, and these cycles come in no particular order. And this is the combinatorial meaning of substitution into the exponential generating, into the exponential series. So this picture is an illustration of this identity. Permutations are equivalent to sets of cyclic permutations. Quite analogously, an endo function. Here's a picture of an arbitrary endo function. Maybe to go back and look at the way I drew this picture for a permutation, I said, okay, a permutation is a bijection from a set to itself. So for every vertex, I'm going to draw an arrow from that vertex to its image under the permutation. And you get a directed graph in which every vertex has in degree 1 and out degree 1. You could draw an analogous graph for any endo function, any function from X to itself. What do you get? You get a directed graph in which every vertex has out degree exactly 1, but the in degrees can be large. And if you draw this directed graph, it will decompose into a finite set of connected components in the undirected graph sense of connected components. So this endo function has 3 connected components. So that's another instance of the same combinatorial decomposition of an object into a set of objects of a different kind. Well, what about a connected endo function? That looks kind of like this. From every vertex, you can follow the arrows, and since you're on a finite set, you'll eventually get caught in a cycle. And since this endo function is connected, the graph will have exactly 1 cycle. So if you then delete the edges from that cycle, you'll have a graph with no cycles. Each connected component will be a tree, and each connected component will have exactly 1 vertex on the cycle. So you end up with a cyclic permutation of a set of rooted trees. So what about a rooted tree? A rooted tree looks like this. It's just a connected graph with no cycles and 1 designated special vertex. If I remove that special vertex and sort of separate it from the rest of the graph, what I get is a single vertex by itself and a set of rooted trees on the other side of this boundary. So a rooted tree is equivalent to a root vertex and a set of pairwise disjoint rooted trees. So these are instances of the kind of combinatorial operations that get translated into algebra with good effect. So this is the sort of first case of that. If every B-type structure can be decomposed uniquely as a finite set of pairwise disjoint A structures, then B of x is equal to x of A of x. This was the relationship between permutations and cyclic permutations, or endo functions and connected endo functions, or graphs and connected graphs. It's often useful to use this equation the other way around. For instance, for graphs. From first principles, we had the generating function for graphs was what's inside the parentheses here. And since graphs are sets of connected graphs, well, g of x is x of q of x. Q is the class of connected graphs. So you turn that around. The exponential generating function for connected graphs is the logarithm of this, which is slightly horrible, but if you wanted to, say, truncate it at up to order 30, then you can do the calculation quite quickly. And you can even throw some more information in there. Instead of having 2 to the n choose 2, if you have 1 plus y to the n choose 2, you can interpret it as saying, for each of the n choose 2 possible pairs, take the term 1 if that pair is not an edge, take the term y if that pair is an edge, and you get, in the exponent of y, the number of edges of the graph. And that goes through the, that matches up on both sides of the equation just as nicely. So you can then extract these coefficients and figure out, for every value of n, what is the distribution of the number of edges of a connected graph with n vertices. And one of my favorite conjectures is about that polynomial. Well, the exponential formula is the first special case of this more general formula, which I'll illustrate in a moment with something we've seen. So for classes A, B, and J, if every B structure can be decomposed uniquely as a finite set of pairwise disjoint A structures together with a J structure on that set, then you get this functional composition formula for exponential generating functions. And this was the relation between rooted trees and connected endo functions. See, if K is the class of connected endo functions, R is the class of rooted trees, a connected endo function is equivalent to a cyclic permutation of rooted trees. And so you get this equation on their exponential generating functions. You just substitute the generating function for rooted trees into the generating function for cyclic permutations. And then one more step an endo function is a set of connected endo functions, so you can apply it again, and you get this quite surprising relation between endo functions and rooted trees. And in fact, if you take this line of reasoning a little bit further, you end up with the second proof of the formula for rooted trees that I'm not going to show you.
I just understand. I mean, is this stuff you're showing us, obvious or heuristic or deep? Forgive me. These relationships.
Right. I would say at the level that I'm showing it to you today, it's purely syntactic.
You're going to be using this implicit function formula on these kinds of things in a moment, so it better be more than that, I guess.
Well, yes. I'm going to basically it's kind of a split level operation. You use the exponential generating functions to analyze the combinatorial structures involved and to get functional equations for these power series. And then those functional equations are the input to the Lagrange implicit function theorem. So the two techniques are actually quite well separated in the way the problems are solved. But yeah, certainly everything I'm saying today, if it's done at an appropriate rate, it's good for third-year undergraduate students. But at some level, the foundations are deep. I mean, so.
So you're basically giving us a kind of simplified version of the species theory of your
without
Montreal
species.
colleagues.
Yes, yes. I'm basically doing species theory without any categories. Yeah. So the foundations that I've described are kind of phenomenological. They're not really telling you what the really root axioms of the theory are.
I thought that one of the difficult things in combinatorics is not only counting things but also having bijective proofs of.
Well, yes, that's
Is
the
there
thing.
an automatic way to because I think there is there bijective proofs of Lagrange?
Yes, yes, there is.
An automatic way to.
The thing is that there is no natural bijection to prove Lagrange. You have to put in some arbitrariness beforehand and then do things relative to some arbitrary choices. So there's no categorical proof of Lagrange. Yeah. I would say, yeah, the technique that I'm showing you today is good for generating these numbers, but if you wanted to actually say, okay, I've, as a result of some computation, determined that there's the same number of these objects as those objects, it gives you very little idea about how to construct a bijection between those two sets.
Or let me re-ask that question. Even if you have a bijective proof of Lagrange, does it follow that you can use that with a particular application of Lagrange to get a bijective proof for that application? I don't see that.
It's not clear because the coefficients that enter might get, well, perhaps you could, yes. Perhaps you could take your favorite bijective proof of Lagrange and reverse engineer it somehow to get a bijection. But it wouldn't be worth the effort because it would not be a natural bijection. Yeah.
Is there extensions to Lagrange where somehow a coefficient would express the set of elements counted by that coefficient?
Yes, there's an interpretation of generic exponential generating functions where it's the sum, n goes from 0 to infinity, f sub n, x to the power n over n factorial, where the f sub n's are themselves indeterminates. So anything you can prove at that level of a generality is going to be true always. And that's exactly how the proof of Lagrange goes.
Well, what if you took f sub n equals a finite sum of indeterminates?
Sure, yeah, because you can specialize independent indeterminates however you like. Yeah.
I mean, I guess that's.
And then you might have a bijection between terms containing
between terms of monomials in this alphabet of indeterminates.
That's how the bijective proof of Lagrange works.
Oh.
Exactly. It sets up a bijection, and then the monomials that appear on one side are in bijection with the monomials that appear on the other side. Yeah. Yeah.
So, maybe the main reason that you, at the very beginning, allowed K to be an arbitrary commutative ring containing the rationals, you want to allow K might be itself a ring of formal power series that count other things with weights.
Yes, exactly. I mean, that's where did, yeah, that's, so in this example here, I would need K to include the indeterminate Y, for instance, yeah. So basically, you can pack as much information as you want into K. I'm in no particular rush. I mean, it just means that the last 5 minutes will go excruciatingly fast. Okay. So before I do a simple example of how Lagrange works in practice, I just briefly have to show you what do these elementary arithmetic operations correspond to combinatorially. So the sum of two classes A and B is the set of structures that are either a red structure of the first type or a green structure of the second type. So for instance, a structure in the class S plus R, where S is permutations and R is rooted trees, it's either a red permutation or a green rooted tree. Either of these things is a legitimate S plus R structure.
Why do you have to make them red or green?
Why do I have to make them red or green? So that I get this formula. See, if I had an S plus S structure without the colors, it would either be a permutation or a permutation. And I want this to hold. So I need the color to get the correct factor of 2 if the structures are the same. And it might be that I have a forest plus a tree. And in that case, the tree might be considered as a forest. So the coloring is just to ensure that the factors are disjoint, so that this really does correspond to summation. Product of class is a bit more intuitive. What you do is you arbitrarily partition the set X into two pieces, and you put an A-type structure on one side and a B-type structure on the other side. So here's a structure in the class S times R. It's a permutation on one side and a rooted tree on the other side. And this boundary can go anywhere. It's just any subset of X and the complementary subset of X. Arbitrary choice.
And again, you
for subset.
say what S is so you know which is which.
Yes, yes. So you have, well, from this permutation, one of the axioms says you can determine what is the vertex set of this permutation. And that will tell you which side that lives on. So this is, if you're going to do an exercise, this is the best exercise to do for starters. Prove for yourself that with this definition, the exponential generating function of A times B is the product of the generating functions of A and B. That's a very nice little exercise. Okay, so here's how to count rooted trees. So remember from the picture we had before, a rooted tree is equivalent to a root vertex and a set of disjoint rooted subtrees. You can express that in this language algebraically. R is equivalent to a root vertex and a set of rooted trees. Here's my root vertex on one side of the boundary and a set of rooted trees on the other side of the boundary. Okay, and now we can turn that into a functional equation just by using the rules that I've mentioned. This is, I mean, and syntactically, it's they even look the same, right?
Well, it helps that set is ensemble, which is the same as exponential.
Yes, and there's good reason for that. It's because that appeared in the original paper by André Joal. Right, so he didn't even have to make an unnatural convention to do that because he wrote that paper in French. So this is exactly the kind of functional equation to which the Lagrange implicit function theorem applies. And it's a one-line calculation. the coefficient of x to the n in R of x. Here I'm going to take f of u equals u, so it's the simplest case. You just apply it here, and then use the delightful fact that x of u to the power n is x of nu, expand that as a Taylor series, and pull out u to the power n minus 1. Here's the coefficient. And so the number of rooted trees on an n-element set is n factorial times this coefficient because of the way exponential generating functions work. That's n to the n minus 1. So that's the prototypical example in this theory. I'm going to use it a little bit later on in this example, which is a bit more substantial. So this, this is an interesting and non-trivial class of structures. Nested set system, it's a pair x delta. X is just there so you can recover the vertex set. And delta is a collection of subsets of x with the following property, that the sets don't cross one another. Any two sets A and B in delta, one is contained in the other or else they're disjoint. So the sets are nested within one another. They never cross non-trivially. So let n be the class of nested set systems. It's not hard to see that the number of these things depends only on how many vertices there are. And, well, you can tell from the first coordinate what the set of vertices is. So here's a picture, just to give you something to think about. Here's a picture of a nested set system on the vertex set X. You can have one-element sets. You can have many sets. You can have vertices that are not in any sets. You could have the empty set. Now, properly, this should be drawn contained in all of the other sets, but that's hard to do. So I just drew it there. So this is an example of a nested set system. How many of them are there? So I'm going to use this generating function with an extra variable in it, keeping track of the number of sets in delta in the exponent of y. If I set y equals 1 here, this summation is going to sum one summand equal to 1 for every one of these guys. So at y equals 1, this reduces to the cardinality of the set of nested set systems with n vertices. But it'll be useful for the recursions that I'm going to derive to have a different variable there. Okay, so that's just saying what I've said. Okay, so now comes the difficult combinatorics. You have to analyze this kind of structure into small enough pieces that you can get some functional equations that are useful. Looks like a mess. Well, the first thing to observe is that these sets of size 1 or 0 are kind of irrelevant. My set system is not going to fail to be nested if I delete all the sets of size 1 or 0. And conversely, if I put in some extra sets of size 1 or 0, it won't fail to be nested either. So you can just say, let's look at the subclass of nested set systems that have no sets of size 1 or 0. And this is like the essential part of the set system, because you can kind of arbitrarily throw in some sets of size 1 or 0, and it's not going to change anything. The thing will still be nested. So what's the relationship between the class of nested set systems and the entire class? Well, start with an arbitrary proper nested set system. Then every time you've got a vertex, you can either include that one element set or not, and that's what's going on here. Every time you have a vertex, you can either include that one element set or not. That's what this is saying. And then for the empty set as well, you can either include the empty set or not. So this functional equation relates the generating function for all nested set systems to the generating function for proper nested set systems. Now what about proper nested set systems? That's what this thing is. That's what it looks like. It's a set of things, blobs. It's a set of blobs, and each blob is either a single vertex or I call it a cell. This is a cell here. And by a cell, I mean a proper nested set system so that the entire set X is one of the sets in delta. So this is the cell membrane, right? And if you look at this picture of a arbitrary proper nested set system, well, it consists of it's a set of blobs. Each blob is a singleton or a cell. And that translates into this functional equation, or into this combinatorial relationship. A proper nested set system is equivalent to a set of things, each of which is either a singleton or a cell. And by algebra, this is the corresponding relationship among the power series. Well, what about cells? How do you describe this cell in terms of smaller pieces? Well, you rupture the cell membrane, and you look at the protoplasm. That's a bunch of stuff too. It's a bunch of singletons and a bunch of smaller cells. But there are some things. It's a proper set system. But there are some things that it can't be. It can't be empty, because my original cell was not the empty set. It can't be a single one of these guys, because my original cell was not a one-element set. And it can't itself be a cell, because I just ruptured the cell membrane. The cell membrane is not there. So that gives you this functional equation. I didn't define this difference of classes, but it turns into difference of formal power series. Basically, this says a cell is equivalent to any proper set system that is not a zero-element set or a one-element set or a cell. And you translate that into a functional equation. And you have to remember an extra factor of y here because of the extra cell membrane, an extra set that went around everything. Right? So this is what the left-hand side looks like without the y. And on the right-hand side, I multiply by a factor of y, put this new set around there, and I get a cell. So,
You subtract out just one.
well, actually, you have to think of this class of structures as being a subclass of this class of structures. So everything of this form is of this form. And so you just look at everything that's of this form, but not of this form.
The three things you subtract are distinct.
I see. I see. I misunderstood the question. Yeah, this is zero-element sets, one-element sets, and cells. Cells have to have at least two elements in them. Yeah, it's important not to double count things. That's the most common error that people make, is double counting things. Okay, so I think that's all the combinatorics in the analysis of this problem. We've come to these three equations relating the exponential generating functions. This is nested set systems in terms of proper ones in terms of cells, and cells in terms of proper ones and cells. So you just monkey around with this for a bit. First of all, let's rewrite this one to isolate Q and M on opposite sides. So I write Q in terms of M, and then I can substitute it in here. And I get this generating function for M in terms of itself, which is the kind of thing that Lagrange applies to. It's a recursion satisfied by the power series M. But it's a little bit unpleasant. You just monkey around with it as much as you can. What I did going from here to here was, well, I took this part, x of y over 1 plus y times m, and I isolated that. And then the rest of the junk on the right-hand side is here. And then there's this thing that's being exponentiated, so I multiplied both sides by y over 1 plus y. So I got that thing again here. And there's the y over 1 plus y. So there's nothing algorithmic about this. You just have to look at any particular case and use some ingenuity. So the nice thing is, let's make the substitutions. R is this power series here, and Z is this power series here. Right? Then I get R is equal to Z times X of R. Yeah. Right? I know how to solve this. We just did it. The Taylor series looks like that. I'm using K as the index of summation. Okay, so that's R in terms of Z. Well, now let's write everything out in terms of the original variables. Something non-intuitive. And I really wanted N, didn't I? So there it is. Here's a formula for the exponential generating function for nested set systems. Well, I really only want the numbers. So let's substitute y equals 1. Starts looking a bit simpler. And now I want the number of set systems. So n factorial times the coefficient of x to the n in this turns out to be that. That's the answer.
Is that an integer?
Yes, that is an integer. This is a horribly, horribly slowly converging series. I just checked it out. This is probably too small to read, but so here n goes from 0 to 19. I've truncated that series after the 500th term. Here's the partial sum up to the 500th term. You're getting good engineering accuracy, even down to about there. But then the 500th term, when n is 18, the 500th term is still 155. When n is 19, the 500th term is 77,000. So it's an integer, but I don't know which one. Anyhow, so that's it. I mean, that's my little introduction to exponential generating functions in Lagrange. Yes?
Just your subtraction, when you did that, how did you avoid subtracting red things and green things, and green things and red things?
Well, this is one of those points where I can't answer that question because I gave you insecure foundations for the theory. But the correct foundations of the theory do it properly. And basically, you can only define the difference of two classes if the one that you're subtracting is embedded into the one you're subtracting from according to a natural bijective correspondence. And then you're guaranteed that you never subtract things twice or not enough. Yeah. Yes?
Could you put back the formula for the n sub n so I can admire it? Thank you.
This is in Sloan's online Encyclopedia of Integer Sequences. Yes?
This question may be out of bounds, but you gave a very beautiful structure for an endo function. If the set is infinite, is there a complete story there?
Yes. There are basically, if you have an endo function, let's say on a countable set, is that big enough? Okay. An endo function on a countable set decomposes into a set of components, and the finite components are of the type I showed. The infinite components have either a one-way infinite path or a two-way infinite path, and then a bunch of rooted trees stuck to that. So you either have something that looks like the natural numbers with rooted trees stuck on it like that, or something that looks like the integers with rooted trees stuck on it. Those are the only things that could happen. You can't have a cycle of infinite length. A cycle of infinite length ends up being either this or this.
You have two infinite branches?
Oh, yeah, I guess these trees here could be infinite trees. Yes, right. Right. So where does this come? If this tree is infinite, then you use the Koenig infinity lemma. Oh, wait a sec. Yes, then this vertex will either have finite in degree or infinite in degree. if it's got finite in degree, then one of these branches has to be infinite by Koenig's infinity lemma. And you can find an infinite, then you can find a component like this. Otherwise, it's got only finitely many, otherwise it's got only finitely many in degree, and each of the subtrees is finite, and then it'll stop. So I believe what I said is true about the spine of these things. But the stuff coming off of here, it could be infinite. In that case, well, if you had a one-way path with an infinite tree on it, then you just take a look at the first infinite tree. This is finite, and then you can do the same thing. So, I think you get infinite trees only on a two-way branch. But you could have several infinite trees on there. Maybe the components are more complicated. Yeah. So, yes, your question is out of bounds. Yeah.
That early exponential generating function result where a of x equals x plus b of x, what was the history of that in brief? Who first proposed that?
I don't know. It's lost in the mists of antiquity. I don't know. I really don't know. I mean, it's hard to know where the theory of exponential generating functions begins. There's this big paper of André Joyal in 1980, but people were doing exponential generating functions long before then. So I really don't know the history of the subject well enough to say who's responsible for that. But presumably, it was the first person who ever thought of exponential generating functions. Yeah.
The first clear statement seems to be in a paper by two physicists.
Trust you to say that.
By who? Ford and Uhlenbeck, I think.
What? There's something like it in a paper of Whitney's, actually.
50s
I just wondered if that was the...
Which paper of Whitney's?
Isn't it the... I forget which one now. One of those ones in the 1930s.
It's not Meyer?
I'm not sure.
There's that one,
Don't quote me.
It must be Meyer.
a logical expansion in mathematics. That's, no, that's inclusion exclusion. Yeah.
That's the one. It's the other long one. What's it called?
It must appear in something by Poya, I'm sure. I'm sure Poya was aware of it.
Does the coefficient of k have any meaning in this formula?
Coefficient of k.
I mean the kth term, I'm sorry.
Oh, the kth term. No, I mean,
It's not an integer.
It's not an integer.
No,
You
they're-
have to have this infinite sum.
let's see, where is k coming from in this formula? It's the index of summation here. So this is coming from the kth term in the Taylor series for rooted trees. So in order to interpret the kth term in here, you have to understand what in this formula is corresponding to a rooted tree with k vertices in this recursion. And it's just really messed up. I don't...
Well, isn't it just you go to a depth of k in your, you are allowing only the sets?
Yes,
Of
but
MK.
the difficulty is that the variable that's recording the number of vertices in the tree is this. And so interpreting in terms of your original variables, x is counting vertices of the set system, y is keeping track of sets in the set system, z is this bizarre combination of vertices and sets, and this is what the recursion is performing its recursion on. It's really... So somehow a nested set system looks, if you squint at it, like a rooted tree, where this variable is that. Yeah.
Who first did this example of nested set systems? It's amazing.
I don't know. The derivation that I showed you, I did preparing for my graduate class a few years ago. But like I say, the numbers come out in Sloan's online encyclopedia, and there are references there to something about phylogenetic trees. And I'm sorry, I can't remember who the authors are of those papers. There are maybe 4 or 5 people altogether. I can get you their names if you really want them. Yeah.
Is this, how fast does this grow asymptotically?
Fast? It's at least, I mean, I'm pretty sure it's super exponential, but I don't know for sure.
Into the end, maybe?
Maybe. I mean, it's hard to say because, I mean, I just computed the first few, and I don't know. I'm not an expert with asymptotics.
Well, the graph looks like a straight line.
Yeah, so
if you had on
it's
the
somewhere
decimal
somewhere between 100 to the n and 1,000 to the n, right? But then it's gonna go even bigger down here.
Could you put up the slide that shows the basic theorem for the 3 classes that gives the recurrence?
Oh, this one?
No, if you about 2 or 3 back where the 3 that relates to 3 set systems.
ABJ.
Oh, that one. Yes. The composition.
The composition, yeah, the composition. The second one.
Where is it? Oh, it was way back. There we are.
Yes, so we have so the J structure on Y, where Y is considered a set.
Yeah. So for instance, say for a connected endo function, you've got a collection of rooted trees. And then you think of these things as being elements of a set, and you put a cyclic permutation structure on that set.
Oh, okay. So to decompose each B structure into disjoint A structures, you have the A structure as a rooted tree, and the J structure on Y is the cyclic permutation.
Yes, that's right.
And then the exponential formula is just the special case where J is ensemble.
Yes, exactly. So one thing I didn't mention, the very last thing, some references. Andre Joyal's original paper, Goulin and Jackson, monumental book, Combinatorial enumeration. Combinatorial species and tree-like structures, Bergeron, Labelle, Leroux. It focuses on exponential generating functions and the underlying theory quite strongly. And Richard Stanley's second volume of Enumerative Combinatorics also discusses this in detail.
Perhaps exponential generating functions appeared in the commands book.
Perhaps, yeah, I wouldn't be surprised. Okay, it's good.